Hello, yes, am I audible?
Yes, sir.
Okay. So in the last class, we discussed about the implementation of gates and logic expression using NAND and NOT gate. Okay, so we already discussed this thing. Now, and today we start with one more important topic, that is multiplexer. So, what is multiplexers? As the name suggests, it is used to multiplex the data. It is used to multiplex the data. What is the meaning of multiplex? That means combine the data in a way that no data will affect. Okay. Simply for example is, if I have a two data, I have to transmit the two datas. One is the data one is the data two. If I want to transmit two data on a single wire, okay, why have we call that as a channel? So what is the best possible ways? One way is that we can add the data one and data two. Okay, then transmit it to a channel. Okay, transmit it through a channel. Now the problem in that scenario is that if, for example, I just say that data one is the 1 voltage 3 volt, data two is 1 voltage 5 volt. If I combine these two data, so what is the data overall is the 8 volt. Okay, I can transmit this data on a channel. At the receiver, I receive the 8 volt. Now, this particularly 8 volt is the combination of two data, data one and data two. Now, it is quite typical that how can I separate this two? Convert into two data. Either I just convert into the 4 volt and 4 volt. So, this particularly become the 1 volt higher as compared to transmitted. And this is 1 volt lower as compared to transmitted signal. Okay, so basically I can say that my data will be changed. So this is the way one. Okay. The second way is that this is a channel. Okay. I just use that data in a way, like for example, I just send a data, this one for 10 seconds and this one for 10 seconds. So for the first 10 seconds, data one will be transmitted. After that 10 seconds, data two will be transmitted. After that, again data one is transmitted. After that, data two is transmitted. Okay. And at the receiver, what we receive? Initially, we receive the data one, then data two, then data one, then data two. So we are getting the exactly the voltage or basically the signal that we transmit from here. If we transmit a 3 volt from here, if we transmit a 5 volt from here, so initially we receive the 3 volt, then we receive the 5. Okay. So we use our channel in a way that it can transmit both the data, but that particularly transmission doesn't affect any signal. Okay, so we combine the data in a way that no data will affect. So this particularly is called the multiplexing.
Sir, one question.
Yeah.
Like for if we send data one for a particular amount of time and then data two for a particular amount of time,
Mhm.
then uh, at the sender and receiving end, their clock should be synchronized, right? Like
Yeah,
they should
clock
have.
multiplexing. So
Okay.
actually the multiplexing will be, if we are going with the more detail, so multiplexing will be done in three different ways. One is the time division multiplexing. Okay. In
Okay.
that particularly what we do, we allot one time period, T1 time period for data 1 and T2 time period for data 2.
Okay.
Okay, T1 then T2. Okay, so this is called the time division multiplexing. Now the problem with the time division multiplexing is that we required a synchronization. Why? Because if I receive this data after a delay and I assume that this is my data 1,
Right.
this transmitted data is data 1, but I receive that it is a data 2,
Right. Right.
and data 2 will be considered as a data
Data.
1. So what I transmit in data 1 is 3 volt, but I received here is the 5 volt, and what I transmit in data 2 is 5 volt, and I receive here is a 3 volt.
Right.
So basically for that one, the synchronization is required.
Okay. Okay.
Okay.
Okay.
Second is the FDM, frequency division, frequency based multiplexing. Okay. Now the problem with the time synchronization or time multiplexing is that if I transmit the data 1 and at that time I have to transmit the data 2 also. So there is no option. We have to wait for data 2. When the data 1 transmission is over, then we transmit the data 2. Okay.
Right.
So in that particular duration, you can't transmit data 2. In the data 1 transmission, you can't transmit the data 2. Initially, data 1 transmission is done, then data 2 transmission is done. And similar problem is that in the duration of data 2, you can't transmit data 1.
Right.
Okay. So this problem will be overcome with the frequency division multiplexing. But this is in more detail of when we going the multiplexing and when we going uh, with the communication part. Okay, but generally in the digital system, what we do, we are basically only, because there is no frequency component is there. So what we do, we are only the time multiplexing we done.
Okay, sir. Okay.
Okay, in basically when the only data bits are available, so we only do the time multiplexing.
Okay, sir.
Okay, like similarly, if we are saying that in a computer, like for example, one server is available. Okay, and with this server, multiple computers are available. Computer 1, computer 2, computer 3. Okay, in that way. Okay, computer 4, computer 5, computer 6. I think in when you go any institute or basically, so there are bus communication is one bus communication protocol is used. So you transmit the data on a single bus, and according to this bus, the data will be transmitted, and again it will be from the computer, it will be transmitted to the server. Okay, so only one bus is available. Now the problem is that again, if I want to transmit, all the computer transmit the data at the same time. So how we basically do the multiplexing? We basically do the multiplexing on the basis of time or bits. Okay, like C1 want to transmit the 4 bits, so initially it will be allotted C1. Then C2 want to transmit at a 5 bits, so C2. Then C3. In between them, we require the C5 will be transmitted to C5. So we allotted a time period on the basis of every computer, so they will transmit the data in that particular time. Sometimes we see that one mail will be sending, and it will be after clicking on the send, it will be directly received on the receiver side, and sometimes it will be take time. Why? Because of this particular time multiplexing.
Okay, sir.
Okay.
Okay, sir.
The multiplexing, if you go in the more detail, the multiplexing will be done in the telephone exchange. Even though if you are going a broadband connectivity, so there is the multiplexing is also done. Okay, like for example, I just required a broadband connectivity. So this is my server room. Okay, from this server, I want to transmit the data up to the 10 kilometer. And in that 10 kilometer, there are the 10 houses, house 1, house 2, house 3, okay, house 4. So like multiple 10 houses are available, house 10. So what we do, either we install a particularly cable from server to the houses, every houses. This is the one way. Okay. But for every connectivity, we require a 10-kilometer cable. The costing for the installation is very high. Okay. Second way is what? I just use one cable, and through this multiplexing, I can transmit all the houses data. So from this cable, a single cable, I can use this one, this one, this one, this one, and this one. Okay, so with a single cable, I just multiplex all the 10 houses data, transmit on a single cable, and after that, here we use the demultiplexers. Okay, the reverse process of the multiplexing. The reverse process of the multiplexing. So one data will be 10 data will be combined in a single, and from the demultiplexer receiver hand, we required a demultiplexer where one data will be distributed in 10 different places. So we can connect all 10 houses with a single cable. So the installation cost will be reduced. Okay. In optical fiber, similarly nowadays broadband connectivity will be done with the optical fiber. So a single optical fiber will be used for the connectivity of 64 houses. Okay, so these are the basically examples where we nowadays practically use the multiplexings. Clear? Any doubt?
No, sir.
Okay. So the multiplexers. Okay, as I already told, multiplexer is a device that will be used to combine multiple data on a single. Okay, so this is a multi-input single output device. Multi-input single output device. Okay, now in the case of multi-input, we have a 1, 2, 3, 4, 5, 6, 7, 8. So 8 inputs is possible, one output is possible. Okay, 4 input is possible, one output is possible, one output is there, 2 input is possible, one output is there. Okay, so multi-input is that is always in the power of 2 raised to power. Okay, if you want to create a 7 cross 1 multiplexer, that is not possible. The only solution in that way is that you need to connect one particularly pin as a ground set. That means you can't apply any input on that one. Okay, so now the possible input is 7 and the output is 1. Okay, but practically it is not a correct because 7 cross 1 multiplexer is not possible. Clear? Any doubts? Okay, now which input goes to the output, that will be decided by a select line. So there are three, or basically n control line or select line is there. On the basis of this one, 2 raised to power n input is possible and output is 1. Okay, so that multiplexer is called a 2 raised to power n cross 1 mux. Clear? Any doubt? So initially we started 2 cross 1 mux. So basically 2 inputs. One output is okay. And to control a 2 input, we required only one select line. That is called the S node. I not input not 0, input not 1, and Y. Now, when the S naught is 0, okay, so basically I naught will be connected with the Y. Okay, and when, so basically if I say that if S naught is 0, output Y is nothing but I naught. And when S naught is 1, output Y is I1. Okay, so finally expression, if I am talking about this one, so the output Y equation is nothing but I naught S naught bar or S bar plus I1 S1. Okay, you can put the value of S naught and S1 and select that Y is equation is correct or not. So if S naught is 0, so this become 1, this becomes 0. So this is 0 and this is 1. So Y is I naught when S is 0. And when S is 1, this one is 0 because S1 bar, S naught bar. So it is a 1 bar is 0. So this term is completely 0. This one is I1. So Y is I1 when S is good. Okay. In the same way, we can design a 4 cross 1 mux. So that means 4 inputs and 1 output is possible. So output is Y, I naught, I1, I2, I3. Okay. Now for selecting a 4 inputs, we require a 2 select line. That is S1 as S0. The generalized representation is that this particularly will be represented as a MSB and this will be represented as a LSB of the select line. Now condition is that S0, S1 and Y. If both are 0, 0, so that means I0 is connected with Y. If 0, 1, so that means that is a 1. So I1 is connected with select line. If 1, 0, I2 is selected, connected with a select line. And when 1, 1, I3 is connected with select line. Okay. So the final equation of Y is both will be 0. So S1 bar, S0 bar, I0 plus S1 bar, S0, I1 plus S1, S0 bar, I2 plus S1, S0, I3. Okay. Similarly, 8 cross 1 box. Y, I0, I1, I2, I3, I4, I5, I6, and I7. If 8 input are here, so we required a 3 select line. S2, S1, and S0. Okay, so again remember that this one is the MSP, this one is the NSP. So S2, S1, S0, Y. So if all are 0, I know disconnected. 0, 0, 1, I1 is connected. 0, 1, 0, I2 is connected. 0, 1, 1, I3 is connected. 1, 0, 0, I4. 1, 0, 1, I5. 1, 1, 0, I6. And 1, 1, 1, I7. Okay, the equation we can draw that it is a S2 bar, S1 bar, S0 bar, I naught. This one S2 bar, S1 bar, S0, I1, S2 bar, S1, S0 bar, I2, S2 bar, S1, S0, I3, S2, S1 bar, S0 bar, I4, S2, S1 bar, S0, I5, S2, S1, S0 bar, I6, S2, S1, S0, I7. And if we add all these 8, so we are getting the final output. Okay, because output is 1. Only output 1 is possible. So what we do, we have to use the OR gate to add all this. Okay, if we are going to the internal circuit diagram of that MUX, so I just draw a 4x1 MUX circuit diagram. The expression is Y is S1 S0 bar I naught plus S1 bar S0 I1 plus S1 S0 bar I2 plus S1 S0 I3. Okay, so we have two select line. So I'm just taking this is my S1, this is S0. Okay, we required a complement also, so we required a complement. We required a complement. Okay, now and so S0 bar, S1 bar, I naught. Okay, second AND gate. S1 bar, S0 is this one, so I'm taking the S0, I2. Third, S1, S0 bar, I2, and fourth one, S0,
No, the second one would be I1.
sorry, I1. And this is I3. Okay, so we are getting 4 terms, 1, 2, 3, 4 with the help of 4, 3 input AND gate. Now what we required? We required an OR. So if I can use a 4 input, so I can combine all 4. So this is my Y. Okay. If we take one particularly, hmm, if we are taking that, this is my S1, 1001011. This is my S0, 10 10 10 110. Okay. With respect to, I am getting the I0, I1, I2, and I3. Yeah, this is my four data I0, I1, I2, I3. Now, can you draw what is the output Y? Okay, so what is my output? Initially, This is my output. So initially we are assuming that this is my, I'm not taking that because we don't know the data. I'm just taking. Now first we check what is the S1 and S0. If S1 and S0 both are 1, so that means which data will be transmitted? If S1 and S0 both are 1, so you can say output is nothing but Y3. Okay, I3. So I3 is this one. So my data will be this one. Okay. After that, both are 0. So when S1 and S2 is 0, S0 and S1 is 0, so I0 data will be transmitted. So in this duration, you can see the I0 data. So I0 data is this one. Okay. At this particularly point, data is 0 and 1. So S0 is 1 and S1 is 0. Okay, so 0, 1. So 0, 1 is the I1 data will be transmitted. What is the I1 data? I. Okay. For the next instance, S1 is 1, S0 is 0. So 1, 0, 1, 0 is I2 data is transmitted. This is the I2 data. So we are transmitting the I2 data. Now again, S0 is 1 and S1 is 0. So 0, 1. I1 data is transmitted. What is I1 data? This one. Okay. Now both are 1, 1. I3 data. This is my I3 data. Now in the last, S1 is 1 and S2 is 0. So 1, 0. I2 data. So if I2 data is available, right now we are not drawing that one. So if you draw here, just wait a minute. Yeah. Okay. So when both are, 1, 0. So I2 data is transmitted. So this is my I2 data. Okay. So this is my final output. Clear? Any doubt?
No, sir.
Okay. Now the similar behavior will be shown by the demultiplexer, but just opposite. Okay. So in the case of demultiplexers, we have one input, multi outputs. Okay, one is the input and multi outputs. Okay, so our input will be connected with which output, that will all decided by the selector. S1 S0, Y0, Y1, Y2 and Y3. Okay, so S1 S0 input, Y0, Y1, Y2, Y3. Okay, so if both are 0 0, oh sorry, I just represent into the higher to lower. Y3, Y2, Y1 and Y0. Okay, when both are 0 0, so basically the input is connected to Y0. So at the Y0 pin, I just connect the input, and remaining is 0 0 0. 0 1, we are get connected here, and remaining is 0. 1 0, we are connecting input here, and all others are 0. And for 1 1, we are connecting input here, and all are 0. Okay, so for this one, I just say that it is a S1 bar, S0 bar times I. Okay, for this one, that is S1 bar, S0 times I. For this one, this is the S1, S0 bar times I. And for this one, S1, S0 times I. Okay, so that is 1 cross 2 raised to power n d max, where n is select time. Okay, so if I am using that in the practical scenario, so basically we have a particularly server. Okay, after the server we use the mux, where we use the different data, combine the data in a single channel, and that particularly channel is a wire. Okay, at the receiver end you have dmux. Now again the data will be separated, and that particularly connected with the node. So node 1, node 2, node 3, node 5 and node 4. Okay, multiple data will be transmitted to multiple node using a single wire. Okay, so the problem is that if we use a multiple wire, so basically circuit is complex. Why? Because 10-kilometer wire, so everywhere you see the wires. Okay, surrounding you, you can see the wires. So basically everywhere is the wire. So first is the complexity reduce. Second, price. If you install a 10 wires of a distance of 10-kilometer or 15-kilometer, any distance, so that will be costing higher as compared to you are using only a single wire. So complexity as well as costing, both will be reduced. Any doubt?
No, sir.
No?
Sir, can you explain this thing again?
Okay. From a server, we are using, we have to install, or basically we provide a internet connectivity to 5 houses. Okay. So what is the way is that from the server, I just install a single wire for every node. So the costing is that, like for example, if the distance between the server and houses is 10 kilometers. So I have to install a 10-kilometer wire for every node. This is the one way. So how much wire is required? The 50 kilometers wire is required because every wire a 10-kilometer length of 5. Okay. Similarly, if we have a 10 nodes, 20 nodes, 40 nodes, so the basically length of the wire will be increased as well as the costing is increased. The second way is that at the server, we have to transmit the multiple data, so we use the multiplexers. Okay, in the multiplexer, what they do, they combine the 5 or 7 or 8 any data, okay, on a single channel, transmitted that particularly information through a wire, and at the point we are getting a demux. Okay, now again demux convert the one information into the different wires. Okay, so the distance between this one and this one, we required only one wire as compared to n wire. If you see that if you connect a, if you take basically just apply for a broadband connectivity, so they will install a wire from a particularly DP. Okay, they call them the DP. Okay, so that from that DP they install the wire from DP to house, not from the server to your house. Okay, they basically in the area they use this DP. This is called the demultiplexing point. DP is nothing but a demultiplexing point. So from that demultiplexing points, they use a wire to install to provide you connectivity, broadband connectivity. But they are not giving you the connectivity from the server. They are giving you the connectivity from the DP to your house.
Okay, sir, get it.
Okay, you can see that when you go nowadays, the broadband connectivity is very common. So when you go somewhere else or walking on the particular road, so on every particular electricity pole, you can see one particularly device is connected. That is called the DP, multiplexing point. Okay, so from that one, if the number of connection is less, so they use the 8-point DP. 8-point DP. That means 8 connection will be provided. That means demultiplexer is 8x1. Okay, the connectivity is more required, so the 16 cross DP, 16 DP is available, 16-point DP is available, 32-point DP is available, 64-point DP is available. So these are the DPs, so demultiplexing point. From that one, they install a broadband connectivity to your house through wire. Any doubt?
No, sir.
If we go the internal diagram of that one, so again we have a S1 and complement of this one. We have S0 and complement of this one. Use S0 bar, S1 bar, and I. This is the value. Okay. If we required a S1 bar, S0 with I, with I, that is y1. If we required a S0, S1 with I with ending, this is y3. We required a S0, so the S0 bar with S1 and I. So this is y. Okay, in the demultiplexer, we required a combined. So we use one OR gate and the data input data is different. But now here the input data is again I. In every particularly AND gate, the input data is I. Only the output will be the difference. So y0, y1, y2. Okay. Now the decoder. The other device is the combinational circuit. Important device is the encoder and decoder. So the basically encoder and decoder is what, like for example, if you are talking about the practical scenarios, okay. So if you want to transmit the data, like I just transmit the data 3, okay, through a computer. So the computer will be converted into the binary data 0, 1, 1, okay, and it will be transmit on a public channel. Public channel, that means that channel that can be used by other also. Now the problem is that any persons can access this data. Now they access this data. I just transmit the data from user 1. This is my transmitter 1. This is my transmitter 2. I have a user 1 and user 2. Okay, and in between them I use a single channel. Okay, so I have to combine the data. We use a mux. 2 cross 1. We have to separate the data, so we required a demux. Now the problem is that if my mux and demux is not working properly, so I just transmit a 0, 1, 1 data. So that 0, 1, 1 will be transmitted on a channel. Now this data will be accessed by this 0, 1, 1 and this also. So a problem is that my data will be received by all the receivers. Okay. If they will use this data, so my information will be passed. Okay, basically my information will be, it will be passed to all the users. So what we do, we use one particularly encoder circuit or decoder circuit to secure my data. Okay, so basically encoder and decoder circuit is used to secure the data. We require some encoding. So I want to transmit a 3, computer will be converted into 0, 1, 1. Now with the particularly encoding and decoding, I can use some other process. So I will convert this data as 1, 1, 0, 0, 0, 1, 1. So what should I do? I just add a 4 bit to confuse the other users. Okay. Now the user 1 knows that they have to discard the first 4 bit and the remaining will be the data. But user 2 doesn't know that this thing. So they will combine this data and decode it. So it is a 11001011. Okay. Similarly, if you are know about that in the mail, some bank will transmit our information. Yeah. So if bank transmit our information, okay. So what they do, like for example, the bank account statement they transmit. So what they do with the bank account statement, they just encrypt that data with a password. Okay. If my mail ID is correct, I will receive that one. But if my mail ID is not correct, so that particularly mail will be sent to other user. Okay. And that user doesn't know the password. So if any information that is passed to any other person who are not authorized to use that information, the information will be protected using the encoder and decoder. Clear?
Yes, sir.
So in the encoder and decoder, not a single input is there. So if you are talking about the encoder and decoder, so encoder is basically 2 raised to power n cross n, and decoder is n cross 2 raised to power n. It is also called the binary encoder. That means other code will be converted into the binary. Okay, and it is called the binary decoder. Binary code convert into the other code. Okay. Now the meaning of that, if I say that we have a 4 cross 2 encode. Two. Okay. So we have a 2 raised to power n input and n output. So this is the n output and 2 raised to power n. Now why we call as a binary encoder is that which particular pin is higher. Like for example, I apply the input I0, I1, I2, and I3. If I apply the input as clearly I0, okay. So according to the I0, if my say I3, I2, I1, and I0. So when my I0 is 1, so we are getting the output as Y0 is 0. Okay, others are remaining 0. If my I1 is 1 and others are 0, so I am getting a 0, 1. If I2 is 1 and others are 0, so I am getting output as 1, 0. And if I3 is 1 and all others are 0, so we are getting the 1, 1. So basically you can see the output. In the output we are getting the binary data. With respect to 0, with respect to 1, with respect to 2, with respect to 3. So we are getting a binary data. That's why it is called the binary encoder. So we can convert any other code into the binary. How we can say the any other code? So basically we know that three number system. In the number system, four particularly different number systems are available. One is the binary, and other is the decimal, octal, and hexadecimal. Okay, so in the octal, what we required the 8 combinations because the data will be utilized from 0 to 7. So that's why we required a 3 output and 2 raised to power 3. 1, 2, 3, 4, 5, 6, 7, 8. So that is I0, I1, I2, I3, I4, I5, I6, I7. So similarly, I7, I6, I5, I4, I3, I2, I1, I0. And we did Y2, Y1, and Y0. Okay. Now, two particular things are here is if not a single input is 1. That means all input are 0. Okay. So that particularly condition is called the invalid condition. Okay, so this is called the invalid condition. Okay. Second scenario is that if more than one input is 1. Okay, more than one input is 1. So like for example, I say that 0, 0, 1, 0, 0, 0. Here you consider two inputs are 1. So that is also called the invalid condition. Okay. So this particularly second condition will be resolved using the parity encoder. Okay. So that particularly is the in upcoming weeks parity encoder. But if more than one input are 1, so that particularly problem will be resolved by the parity encoders. Okay. So this will be resolved by the parity encoder. And this condition will be resolved by when all are 0. So we can say that this is my, the output will be the default condition. If I say the default condition is 0, 0, 0, so output is 0, 0, 0. If the default condition is 1, 1, 1, so the output is 1, 1, 1. Okay, so any particular default condition we set according to this one, that will be giving us the output. Okay. Any doubt?
Sir, could you explain that parity encoder, or is it just a condition that is, it's just mentioned as parity?
Parity encoder, we will cover that particularly part in the upcoming weeks.
Okay.
Okay, so I am not going in much detail of that parity encoder, but this problem will be resolved if we are talking about the simple till week 6. So we are not taking this two condition are the invalid conditions. If
Okay.
all inputs are 0 or and more than one input will be 1.
Okay. No problem.
Okay,
Yes.
but in the upcoming weeks, if two more than one input will be 1, so we will solve using the parity encoder of that.
Okay, sir.
Okay, so we are not covering here because parity encoder will be, I think, in week 7 or week 8, I think so.
Okay, sir. No problem.
Yeah, week 7. So in the next week, it will be the parity encoder. So we will cover there. Okay,
Okay,
but right now, these two conditions are the invalid conditions.
okay, sir.
Okay. Now, similar to the encoder, there are the decoders. That is n cross 2 raised to power n. So, two inputs, the four outputs. I1, I0, Y3, Y2, Y1, Y0. So, I1, I0, Y3, Y2, Y1, Y0. So if both are 0, 0, Y0 is 1. If 0, 1, Y1 is 1. If 1, 0, Y2 is 1. And if 1, 1, Y3 is 1. Just wait a minute. Yes. We have two topics are remaining. One is the three topics: tri-state inverter, delay of the logic, and static timing analysis. So when it will be covered, we will stop the session. Okay, so this is the decoders. Now, if we see the table of that one, so for the Y naught, we can say that is the I1 bar, I naught bar, Y naught. This is the I1 bar, I naught, Y1. This is the I1, I naught bar, Y2. And this is the I1, I naught, Y3. Okay, I naught. Now, if you see that decoder and demultiplexers, where we are already having the 4 output, okay, that particular output dependent on the select line and the input. Here it will be selected dependent on the input lines I0, I1, okay, and according. So everywhere if you see that Y naught is 1, so these are 1, 1, 1, 1 only of that one. So if you see, compare with the decoder with the demultiplexer. So in place of select line S1, I just use the I1. And in place of S0, I use the I0. Complement of that one. Complement of that one. Initially, we have the complement. And we required one more, third input. But right now, the third input is 1. Okay, so if we remove this input, no issue. If we remove this input, no issue. That is a Y0. Okay, if you see that this Y0 equation, that is I0 bar and I1 bar, similar to the Dmux S0 bar, S1 bar multiply with the input. But input is 1 as well, as you know, already know that the input is basically output is 1. So we can say that it is almost similar. Demultiplexer and decoder are the almost similar behavior. Similarly, if we have Y1, Y2, Y3. So basically implementation of 2 cross 4 decoder requires 2 inverter and 4 AND gate. If we have a 3 cross 8 decoder, so we require 3 inverter. Why 3 inverter? Because for the 3 input, we required a 3 inverter complement input also. So 3 inverters, and for 8 output, we required a 8 AND gate. Okay, and similarly for the Dmux also, yeah. For a 1 cross 4 input, 1 cross 4 Dmux, we have a 2 inverter and 4 AND gate. So basically, for the Dmux, 1 cross 2 raised to power n, we require a n inverter, then 2 raised to power n AND gate. For the decoder, n cross 2 raised to power n, we require the n inverter and 2 raised to power n AND gate. So it is somehow different, similar. The implementation of Dmux and decoder, similar somehow. But one important thing with the decoder is that one enable pin is also important. Enable pin. So what the enable pin is do, I just go the truth table of here. Okay, I just say the enable pin. 0, sorry. 1, 1, 1, 1, 0. Okay. Now if you are taking the I0 and I1 any value, either you are taking the 1, 1, 0, 1, 1, 0 and 1, 1, sorry, 0, 0. Your output is always 0, 0, 0. So that means no output line will be high. Okay, no output line will be high, because if your enable is 0, so that means that your circuit will not working. Okay, your circuit is not working, and if your circuit is not working, that means you are not getting any output pin as a high. Okay, the importance of enable pin is when we are going to implement higher order decoder using lower order decoder. So we will cover that one in the week 7. Okay, so when we are going to implement a higher order decoder using the lower order decoder, like for example, implement 3 cross 8 decoder using 2 cross 4 decoder or 1 cross 2 decoder, then the enable pin is very important. Okay. Any doubt?
No, sir.
Okay. Now the next is tri-state inverter. So basically we know the dual state inverter. What is a dual state inverter? Is that this is my inverter that will be operate on a two state. One is the state 0 and one is the state 1. So when we are providing the 0, we are getting 1. When we are providing the 1, we are getting the 0. Third is we are required one more state, and that particular state will be given as a input for this particularly as a enable. Okay, so we require enable, input and output. So if enable is 0, we apply anything as a input, we are getting as a high impedance state, Z, high impedance. Okay, if we provide a 0 enable 1, then input is 0, output is 1. If we provide enable 1, input is 1, output is 0. So we are getting a 3 state with respect to 0 and 1. Initially we are getting as output. So 2 state, one is the 0 state, one is the 1 state, low or high level. Okay. Now along with the low and high level, we are getting one more state that is called the high impedance. Okay. Now what is the meaning of high impedance state? We have an inverter. Okay. If we apply 0, we are getting 1. If we apply 1, we are getting 0. Okay. But if we change the input from 0 and 1, always we are getting a 0. So what is the meaning of that one? The inverter. If we apply 0, we are getting 0. If we apply 1, again we are getting 0. So what is the meaning of that one is, may be possible your input will not travel to the output point. Okay. Or maybe circuit will be break. Okay. If there is no properly connectivity between the input and output, what should we apply at the input? We are always getting the 0. Okay. So we can say my circuit is a open circuit. Somewhere here it is a open circuit. Okay, we assume this one only by changing the input. We are observing that no change in the output. So that means there is no proper connectivity between the input and output, or maybe possible that circuit is a open circuit. So current will not passes from the input to output, or we are getting a 0, always 0. And this particularly open circuit has a impedance Z is infinity or R is infinity. Okay, so that's why it is called the high impedance state, where we observe that with changing in the input, we are not getting any particularly variation in the output. The output remains fixed. Okay, this particularly is called the high impedance state. You already observed the VTC, voltage transfer characteristics. If you have a VOH that is 4.6 volt, so your VIL is around 1.3 volt. Okay, that will be considered as a logic 0. VIL 1.3 volt.
Yes.
But if you check with the multimeter, you are getting a 0 volt. Due to some capacitance, due to some particularly battery connectivity, you are getting some voltage, but due to the high impedance state, you are always getting a 0 volt. The logic is 0, but against the logic, the voltage is also 0. You are getting at this point is always also 0. So that particularly condition is called the high impedance state.
Okay, sir. So for that we need the third enable pin to be there.
Yeah, for this one we required a third enable pin also. Okay, that particularly enable pin will be the controlling the third state.
Okay.
Okay, because if you have a one input, so only with the one input only two particularly state is possible, 0 or 1. If we apply the 0, we are getting 1. If we apply the 1, we are getting 0. So if there is no particularly enable pin, so two state input state is possible. With respect to two input state, you are getting a two output state. So to create a third state, we required one more input, and that is called the enable.
So then, the high impedance state, is there a logical value associated with that? Is it 0 or like?
That is not exactly 0, but we are considering that there is no connectivity between the input and output. We are getting the voltage also 0.
Okay. So,
Okay, the logic is 0, but as well as the voltage is also 0.
Okay. Okay.
Now, so if we say that we have one circuit, we have created so basically one more term is fan out. I don't know you are aware with this particular term or not. If we go with the logic designing, logic, okay. So there is one term is the fan out, and one term is the fan in. Okay. So basically, what is the meaning of fan out and fan in is we are getting some output. Like for example, we are getting the output here. Okay. With respect to this output, we are getting a current I1. Okay. Now, if this I1 current is used to operate a four different circuit. Circuit 1, circuit 2, circuit 3, and circuit 4. Okay, that means this particularly output current we are getting at a point, this point, that particularly current is sufficient to operate four different circuits that are connected in a cascade form. So this particularly current is suitable for the 4 circuit. So we can say the fan out is 4. That means how many maximum circuits, cascade circuit, that particularly current will operate. That is called the fan out condition. Okay. Similarly, the fan in is what? What is the minimum current required to operate this circuit? And that particularly current will be getting from the combination of multiple circuit. Circuit 2, circuit 3. So that means from the circuit 1, circuit 2, circuit 3, we are getting a I1, I2, I3 current, and that particularly current I is nothing but I1 plus I2 plus I3. That is sufficient to operate cascade circuit. Okay, that means this 3 circuit current is required to operate this circuit. If any of the circuit is not working, this particular circuit is cascade circuit is not operating. So minimum 3 circuit is required to for a sufficient to provide a sufficient current, so the cascade circuit will operate properly. So that is called the fan-in. So in this case, we can see that 3 circuit is required. So the combination of 3 circuit current will be used to operate this cascade circuit. So that is a fan-in.
Okay.
Okay. So this high impedance state is basically because of this fan-in and fan-out. So fan-in. Now the thing is that we say that fan-in is 3. So that means 3 circuit current is required to operate this circuit. But we connect only 2 circuits. We only connect the 2 circuit. Okay, now what will be happen? If we change the input, from 1 to 0 or 0 to 1, because of not providing the efficient current, this particularly circuit is not working. I am taking one example is that you have a one optical mouse, wireless mouse, and that particularly wireless mouse use required 2 batteries. Okay, 1.8 volt, 2 batteries is required. That is 3.6 volt with some current. I just say the 900 mAh current. Okay. If my current is reduced, so basically I say that after a certain time, my battery start discharging, so the current will be reduced. So if from 900 to I am getting a 750 milliampere current, what will be the happen?
Mouse will not work.
Mouse will be working, but not exactly in a scenario that is the actual operation. Like for example, you see that in the backside the light is glowing. Okay, but when you push it in the upward direction, so it will be go slowly. Why? Because that current is not sufficient to operate that in a appropriate manner.
Okay.
Okay,
Yeah.
again further reduce the current, like for example 600 mAh. You can see your light is not operated in that one, and you can analyze that the battery will be drainage. Okay, battery will completely drain. So you have to change the battery. But intermediate, there is a one state where the current is not less than this particular desired condition, but not up to the required condition. Okay, in between them, there are certain current. So that particularly will affect the working. Not properly that it is not working, but it will be moving slowly. Sometime it will be hang. Okay, so that is because of the fan-in condition, fan-in and fan-out condition. Your required current is not supplied to the mouse, optical mouse, so that will be working efficiently. Is it clear?
Yes, sir.
So that particularly is called the high impedance state. So that related to the high impedance state.
Okay.
Okay, I think delay of the logic gates we already covered somehow, that every particularly gate, if I am saying that I have a AND gate. Okay, basically I am just taking the NOT gate. Okay, so can I draw the diagram of NOT gate using the transistors? Input VCC output. Okay, I just draw this diagram. Now if I say the input is 0, so what happened? Transistor is off. Okay, if I say the input is 0, that means transistor is off.
Okay.
If transistor is off, so that means VCC is connected with the output. Okay, so your output is VCC, or we can say the logic 1. Okay, and when transistor input is 1, the transistor is on. If the transistor is on, all current will be passed from here to here. Okay, and what is the output? The voltage drop across these two is the output. Or we can say that it is a VCC minus the transistor voltage, sorry, the current I RC. Or we can say that if this value is higher, so that will be behave as a 0. Okay, so basically a transistor with this configuration behave as a inverter. You can draw a similar circuit using this particularly transistors for a AND gate. AND gate will be designed. This is a grounded. We are getting A, B, this is the VCC. We require one inverter here. Okay, this is the AND gate. If your A and B both input is 0, 0, I just say this is the Q1, Q2, and Q3. So Q1 is off, Q2 is off. You know the working of transistor. That means if the base current is 0, so we can say that transistor will not working. Okay, so that's why if A and B both are 0, so that means no current is here in the base. So Q1 is 0, Q2 is 0. Okay. So the current that is passed, it is an open circuit. It is an open circuit. So VCC directly connected to the base of Q3. So Q3 will be on. Okay. If Q3 will be on, so the current VCC will pass from 0 to ground, and the output will be the voltage drop across this particular transistor. That is the VCC output is 0.7 volt. Why? Because the transistor VC is 0.7. Okay, transistor VC is 0.7 around something. So we are considered the logic 0. If 0, 1, so Q1 is off, Q2 is on, because here we apply the 1. Okay, but again, there is no circuit between the VCC and grounded. So Q3 is on. VCC will pass on a Q3. If VCC pass on a Q3, again we are getting the 0.7 voltage, that means logic 0. For 1, 0, again this is the on, off, Q3 is on. So we are getting a 0.7 voltage, that is logic 0. And when both are 1, so that means both transistor will be work. So VCC will be passing here, grounded. So the current at the Q3 is 0. If Q3 current is 0, so this is the on, this is on, and Q3 is off. If Q3 is off, so VCC will be passed at the output. So here we are getting a 1 logic. Okay, so we can implement any particularly gates with the help of transistor. Now you know that transistor have some capacitance also. And because of this capacitance, they have time delay. The variation of time delay is possible, but every gate has some time delay. Either I am talking about the all gates that has time delay. If I am talking about the combination circuit is what? Either the DMUX, MUX, encoder, decoder. They are also having the time delay. Why? Because they are also designed with the help of gates. So that is again designed with the help of gates. So again a time delay. Okay, so either every particularly combination circuit we are taking a time delay. Similarly, if we are going with the weak 9 is the sequential circuit. So that is also a time delay. Sequential circuit, that is also a time delay. Clear? Any doubt?
No, sir.
The next is static timing. Analysis. So basically, the static timing analysis is that for every gates we have delay. So static timing analysis basically provide an analysis that what is the minimum time required to get, sorry, what is the maximum time? What exactly maximum? What is the minimum? Time required to get the appropriate output using critical path. Okay, so there are two terms, is that one is the appropriate output and second is the critical path. So what is the meaning of appropriate output and what is the meaning of critical path? Like for example, we have one circuit. This is the A, B, and the circuit with the C, okay, this is my circuit I am taking. Okay, now if I say that the delay for this one is 1 nanosecond, delay for this one is 2 nanosecond, and delay for this one is again a 2 nanosecond. So we are getting the output after a 2 nanosecond. Okay, we are getting the output after a 2 nanosecond. Is it clear? Why? Because for getting the output, only we have to pass from this one. We have to pass from this one. If any input is 0 or 1 here, or 0 or 0 here, or 1 or 1 here, so that particular data will be applied to the NAND gate and we are getting a output after a 2 nanosecond. But this is not a appropriate output. Why this is not a appropriate output? The particularly input you are considering either it is a 0 or 1, but that input is not received through this one, or that input is not received through this one. The second input is it will be passed through the NOR gate, and first input will be passed through the NAND gate, but this output you are considering either 0 or 1, that will not pass through the NAND and NOR gate. So you are getting the output after 2 nanoseconds, but that is not a appropriate output. The appropriate output you are getting when you apply the A and B after a 1 nanosecond, you receive the output of this NAND gate. And if you apply this NAND gate after a 1 nanosecond and apply the C also 1 nanosecond, because so you are getting the output at a here is 3 nanosecond. Why? Because 2 nanosecond delay. Now this 3 nanosecond and after 1 nanosecond, so basically which one is greater? 3 nanosecond. So you apply the output of 3 nanosecond, you apply the input at 1 nanosecond, and it provides the delay of 2 nanosecond. So you are getting a 5 nanosecond. You get the output 5 nanosecond, and that output is correct output or appropriate output. Okay, correct output or appropriate output. So that is called the appropriate output. Okay, now the critical path. Understand what is the meaning of appropriate output? You are start getting the output after 2 nanosecond, but that output is not correct. Because
Yes,
your correct input condition A, B, C you apply here. So after a 1 nanosecond, you are getting output from the NAND gate. After 2 nanosecond, you are getting the output. 3 nanosecond, you are getting the output NOR gate. And when it will be applied to the final gate, you are getting the output after 5 nanosecond. And that output is the correct output with respect to the A, B, and C. Clear? So that's why it
yes,
is called the appropriate output. Okay.
yes, sir.
Now using the critical path. So what is the meaning of critical path? Critical path is that, like for example, I just take one more circuit here. Okay. Now to get the output, we require two inputs. One is input is this one input is this one. Okay. Now we have to check. So there are two particularly path is available with respect to this out. Okay. Now these paths will be directly connected with C. That means this particularly will be taking the 0 nanosecond delay. Okay. The second input will be received from this particularly NAND gate, and that gate is also having a two input. Okay. So which is my critical path? Critical path is the path that will be cover all the gates which are added in between the output and input. Okay. You are having a one path is this one. You are having a one path is this one. You are in this particular path, you are getting the delay at a 0 nanosecond. But with the only C input, you are not getting the correct output. You are getting the correct output when this output is correct. So Y1 is. So from Y to ABC, or basically to recover the value of Y from the ABC, you required a path Y1. Okay, after Y1, you required a path of Y2 and Y3. Okay, and from that Y2 and Y3, this is the Y4 and Y5. And from the Y5, it is the Y6 and Y7. And this is the Y8. So to cover the output, you required Y1. Then after that Y1, you just go to the Y3. Then Y3, you just go to the Y5. Then Y5 to Y6 or Y7. So this is your critical path. That will be cover all the maximum delay that will be added to get the output. Without that particularly path, your output is not possible. Okay, without that path, your output is not possible. So that path is called the critical path. Understood? So your output is not possible with this, without this one and this one. Okay, so that is connected with C. Now, at when you receive at Y1, so your output is not particularly possible without this one and this one, Y2 and Y3. Okay, again Y3, when you go to the Y3, your output is not possible with Y5 and Y4. With the Y5, your output is not possible without Y6 and Y7. So your output Y will be required a path. I just say the Y9. So one is a Y9 directly connected with Y8. So you are getting the output Y. Okay. Y9, then Y8. Second is you go with Y7. Okay, then Y7, this is the Y5. Then Y5, you go with the Y3. Then Y3, you go with the Y1 and then Y. This is the second path. Third path is Y9, then from Y9 to you go Y4. Then from Y4 to you go Y3. then y3 to y1, and then y. Okay. Fourth part y6 to y5, y6, then y6 to y5, then y5 to y3, then y3 to y1, then y1 to y. And the last path is y6, then y6 to directly y2, then y1, then y. Okay, so there are 5 paths available between the input and output. Is it clear? Now, which path require the maximum delay? That is called the critical path. So if we go with y9 and y8, y9, y8, and then y, so 0 nanosecond delay. Okay, go with y7, then y5, then y3, then y1, and then y. So you required a 1 nanosecond delay here, 2 nanosecond, 3, then 2, 5 nanoseconds. So this is here 5 nanoseconds. Third is y9, then y4. Okay, then directly you are getting a 2 nanosecond delay, then y3, then 2 nanosecond delay, so 4 nanoseconds. Okay, fifth one is y6, then y5. So y6, when we go with y6, so 1 nanosecond, then 2 nanosecond, then 2 nanoseconds, so again a 5 nanosecond. And last one is y6, 1, then directly 2 nanosecond, so 3 nanosecond. Okay, so either this one or this one is the critical path. Okay, why? Because the output of this one is dependent on y2 and y3. The y3 will be dependent on this particularly. I say that u2. So y3 is dependent on u2. Without u2, it is not possible to find the final timing or final delay. So u2 is covered in this particularly path, this one and this one. The y5 will be dependent on u1. So u1 will be covered in this one and this one. So all particularly gates will be included in these two paths to get the correct output. So this is called the critical path. Okay. Any
Okay,
doubt?
No, sir. So we can have two critical paths, multiple critical paths.
Multiple name, not multiple, because either you consider the y6 and y7 both will be the input connection. So you can use the y6 and y7. Otherwise, the path will be same.
Okay. Okay.
Okay. Y7 or y6 they doesn't provide the delay now. So either you consider the y6 or y7 both will be the same.
Yeah.
So the path is from the y5 to y3 to y1 to y.
Okay.
The delay will be start from here. From here to here we are getting the delay. In between that y5, y3, y1 and y.
Okay, so it's the path which has the maximum delay, without which the output is not possible.
Minimum delay without which the output is not possible. Correct
Okay.
output is not possible.
Okay. Okay.
Okay, we have like for example we have one more circuit here. 1 knot, 1 knot, 1 knot. Okay, but that knot is not used anywhere. Okay, I just connect it here somewhere. Okay, not in this circuit, some other circuit we will explain that one better. Okay.
Okay, sir.
So that's it for week 6. Just go with the questions part. We will in the next class we will solve that.
Okay, so okay.
If you have any doubt, you can ask. Shall we stop here?
Yes, sir.
Okay. Thank you all.